SMA and renal artery, and obviously aorta, of course. Let me get in a little bit closer here. So I didn't bother. Oh, you know what? I probably could have copied this, flipped it, and put it over on the other side. Darn it, that would have been cool. Would have been, well, I didn't do that, so. All right. So some things you have to know about the arterial system, and then we kind of cheat on the venous system. Now, I didn't draw any veins in on this image, but anything with the arteries, anything closer to the heart is proximal, or at least closer to the source, which would pretty much always be the heart. So this is that's the right renal artery all the way across here, and this would be prox, mid, and distal. And I guess sometimes people get a little confused. They want to say it's a renal artery and they're looking through the kidney. You know, they got their transducer over here. They're looking this way through the kidney, and they want to call this proximal. And I just want you to avoid that. It's always the distal artery is near the kidney. Proximal artery is near the aorta itself. As we go further, this, oh, and by the way, multiple arteries are not unusual. 2, 3, sometimes even more. Obviously, the more arteries you put on there, the more rare that's going to be. So multiple arteries are always available, or always a possibility, and a real pain in the butt for us, but probably good for the patient to have a backup plan in case one artery goes bad. Although having said that, I'll just say this now. Remember when we talked about the spleen? The spleen was divided. In fact, here, let me just draw some temporary lines here. The spleen was divided into all these different parts, right? That'll be enough. The kidney as well is divided into parts, as we're going to see. This causes a bit of an issue if one artery goes bad, one of these smaller arteries goes bad. You could have a, we'll just call it dead. Whoops, I always forget that. We'll just call this one section dead here, but alive up here, alive down here. So what we end up seeing is a scar and everything. The reason I mentioned that is that I just said that, well, you know, maybe having an extra artery is a good thing. It's actually not. It doesn't do us a whole lot of good to have extra arteries going to this organ, because if one artery goes bad, that one section is going to go bad. It does not cross. In other words, there's no anastomosis between each one of these little sections here. Okay, moving on. So this was right renal artery, obviously over on the left on the other side. And then it starts to split into smaller arteries. And let's see, I'll just put a little arrow here. That these, this, here, even the sub-branches here, everything, as long as we're in this yellow area, and I'll tell you what the yellow area is too. Hint, there is a reason why there's yellow. Any of the arteries in here these are all whoops, not segmental. Segmental arteries. First order, second order, but they're still all segmental arteries. And each one, and by the way, so this, I'll give you a little bit of renal architecture because we kind of need to know that too. That's ureter, this whole, well, this is ureter out here. Let's just draw an arrow to this. Pelvis. So the pelvis is the very top of the ureter, or maybe I should say the beginning of the ureter. It can be partially in, partially out. It could be all in, it could be mostly out, and there's different pelvis arrangements. I've kind of drawn a halfway arrangement there. So the pelvis is the, that's the collecting. Our first part of the collecting system is the pelvis here. No, I'll hold off on that. We'll just label pelvis. There's other things to label, but we're going to talk more about architecture tomorrow. And I will say, and most of you probably already know this. Let's just put an arrow down here. That is a renal pyramid. Obviously called pyramids for their shape. And that's part of the business end of the kidney. It's actually all the collecting tubules from each nephron goes through the pyramid, and the collected urine is dumped into the collecting system of the pelvis and down the ureter. Okay, and then, you know what, I guess I'm going to draw, let's draw a line from, I'll just go from here to here. That whole area between the pyramid, actually, well, including the pyramid, including the outside part, all of it collectively is the parenchyma, just like a liver. Parenchyma. Just like the liver, just like the spleen, everything has parenchyma. It's just simply tissue. And so the tissue of this organ kind of goes from the outside to the collecting system. And the collecting system is obviously still tissue too, but it's not considered part of the parenchyma. So the whole thickness is the parenchyma. And I'll hold off on other definitions for now. I really want to stick to, as much as I can, the vascular portion. Okay, so let's see. We've got the renal artery, prox, mid, distal, segmental arteries. And then the segmentals, once they go up into the parenchyma on either side of a pyramid, they are now interlobar. So let's do a arrow like here. This is interlobar artery. All right. Those, and this is a really good one for, I'd say the segmentals and especially the interlobars. These are going to be part of our examination. All right, I don't want to get in too close. My ability to write goes way down real fast. You'll see that the interlobars, like I said, they go on either side of the pyramid and then they arch over, or they arc over. This arc, conveniently enough, is called the arcuate arteries. So each one of these guys at the base of the triangle, triangles are upside down over here, but that's just the way it is. The base of the triangle where it sweeps around, it's called the arcuate arteries. And then I'm going to give you two names for these little jazz hands here, these little fingers sticking out. Your book calls them interlobular arteries. Interlobular versus down here was interlobar. So interlobar and then the little fingers are interlobular. I prefer in what's actually the new nomenclature, so the technically more correct nomenclature is, let's just do that. Cortical radiate. Now, why they've changed the nomenclature, I don't know, but I definitely like it better because cortical, well, this area from the outside the kidney to the base of the pyramid is the cortex, so that makes sense. And radiate, these radiate out into the cortex. So it makes a lot more sense. Interlobular and interlobar can very easily get confused. So I definitely prefer cortical radiate, but just know that you might see both out there in the field. And then as we go even further, actually, and we're not going to do that today, but we go down in the cortical radiate arteries. Those arteries eventually feed the nephron themselves. So our nephrons, the business end of the nephron is up here in the cortex. The collecting tubules are the medullary pyramids. You know what? Let's add that word just because. Medullary pyramid. Okay. Sometimes people just say the pyramid. Sometimes they say the medulla. Sometimes they say medullary pyramid. I think we should probably use everything and figure that out from there. Okay. Now, let's talk a little bit about why we care about the vascular. So one thing I used to do all the time, and I worked at one place and someone got on my case about it. They didn't really have an answer for me. They just said, you know, don't do that. I kept on doing it, but I would just simply, every time I did just a plain kidney exam, I would put color on it. And my theory was, well, it's easy enough. It's one button. You do it for 3 seconds. You get some color on the kidney, and you move on. Well, two problems. One, sometimes it wasn't 3 seconds. Sometimes it was more like, 2 minutes worth of trying to get good color on a person, simply because my equipment wasn't great, or their body habit has just made it difficult. But the reality is, showing blood flow in a kidney doesn't actually tell you a lot, because low pressure blood flow there could be lots of blood going into the kidney, but if it's not at the right blood pressure, doesn't matter. I mean, it's feeding the kidney, but it's not functioning correctly. So that the blood pressure and simply putting color on doesn't tell you anything. It just tells you, yeah, there's blood flow, but big deal. I mean, you assume there's blood flow. It's not if there wasn't, it'd be dead. It'd be a remnant of a kidney sitting in there. So color alone is not all that helpful. I used to do it all the time, and now I realize that it's not so helpful. So let me move in a little bit more. I drew awfully small here. So we're really going to talk about, and I mean barely touch the surface, because this is very complicated. This renin angiotensinogen pathway is very complicated. We don't need to know all that. The kidney is important in maintaining our H2O balance. That makes sense. That's what you pee is, mostly H2O. And therefore, blood pressure. Because the amount of blood you have in your arteries and veins has a lot to do with blood pressure. It's not simply it's not only how strong your heart is or how stiff your arteries are, which causes blood pressure. It's the volume of blood in the system as well. And so if you think about that, if you have low blood pressure, the body's going to react by maintaining more fluid in order to help raise that blood pressure. And the opposite's also true. If you have high blood pressure, the body's going to more or less going to try to get rid of some extra fluid and so that you can bring the pressure down. So, but sometimes the kidney sees, in quotes, hypotension falsely. Hypotension, low blood pressure, falsely. So it thinks you have low blood pressure even though you don't. And Bernoulli is back to get us again. Bernoulli's equation, well, don't worry, we don't have to deal with the equation, but the concept of Bernoulli is back. So about 6% of hypertension patients are of renal vascular origin. In other words, most likely some kind of stenosis. We get our patients from when they're suspected uncontrolled hypertension. In other words, drugs don't work. So uncontrolled hypertension, they're taking blood control medicine, not working at all. Okay, something's going on. They really suspect at that point that it's a stenosis. Children, young adults, especially young women, because women have just in general a little bit less of a chance to have hypertension, although it's not that different. But children or young adults with hypertension, right off the bat, they're going to say, let's think about renal vascular. If there's a bruit, of course, and idiopathic azotemia, which is really, if you've ever, there's the blood, there's a blood test, blood, urea, nitrogen, the BUN, the BUN. When your urea and nitrogen levels are high and they really don't have a reason for it, so in other words, idiopathic, that increase is called azotemia, and this could be an indication of renal vascular, since basically it's like hypertension. We don't know why the blood urea nitrogen is up. Okay, so we have an idea so far that the kidney is seeing hypotension falsely. We know that the majority of hypertension patients, the doctors have a pretty good idea of why the patient has hypertension, but 6% of them, it's kind of a mystery, and so then they go to renal vascular origin, and so uncontrolled children, bruit, and something has to do with stenosis and Bernoulli's law. And I've already mentioned that you could have plenty of blood flow in a kidney and still have a renal vascular origin for hypertension. I guess I'm still over here. So let's talk about that real quick. If there is a stenosis, let's draw my little, get a little drawing in here. I'm going to go ahead and put a stenosis right about here because that's where most of them exist, in the proximal. There's my stenosis. And what happens after a significant stenosis? No, the whole page goes sideways. That's what happens. Bernoulli happens. Significant stenosis down here. Bernoulli. In order for the velocity to increase, that's an increase in kinetic energy. Another energy has to go down. So our blood pressure goes down after a stenosis or at a stenosis, after whatever. The blood pressure goes down and it never comes back up. So your kidney says, oh, the body is hypotensive. And by the way, I'm important. This kidney, I'm important. Whoops, I'll go a little bit higher there. I maintain H2O balance. I maintain blood pressure. At least I'm part of the chain that maintains blood pressure. So I see a hypotensive blood flow. That means the whole body is hypotensive. I'm going to raise blood pressure, and I'm going to be a little smiley face because I am the hero here. I really prefer to have my little cheater here. It makes everything prettier. There we go. Hypotensive. See, it sees hypotensive. It raises blood pressure, and so what happens? The blood pressure goes up. But have we solved any problems? No. Let's see. My blood pressure has increased here in the aorta, but it's still firing through the stenosis at a high velocity. It's still dropping over here. So the kidney still says, oh, I'm still hypotensive. Raise it more. Your blood pressure goes up a little bit more. Blood goes through the stenosis. Blood pressure drops after the stenosis. So in other words, your entire body now has high blood pressure except for the kidney. The kidney does not have high blood pressure because of this stenosis, and so it cannot understand why this isn't working, and so it continues to do this. And it does this through a hormone called renin. Renin. Is it two N's? No, I guess not. Renin is released. Actually, a hormone takes renin and prorenin and makes it real renin. It's a whole thing. Well, for simplicity's sake, renin is released. That renin acts on another hormone called angiotensinogen. That's a T, not an F. Oh, God. I got to fix that. It's driving me crazy. All right. Angiotensinogen. Tension. Angiotension. Ah, okay. Angiotensinogen is a vasoconstrictor. Yes, a vasoconstrictor. So this is what the kidney's doing. It's releasing renin. It's acting on another hormone called angiotensinogen. It's actually mostly in the lungs, but that doesn't matter. Well, angiotensinogen is mostly in the lungs for whatever reason. I have no idea why it's in the lungs. And that is a vasoconstrictor. Vasoconstriction throughout the body, if you're vasoconstricting our little arterioles throughout the body, that raises blood pressure. It also has effects on aldosterone, which is changes the filtration characteristics of the kidney. But for right now, we'll just talk about angiotensinogen as a vasoconstrictor, which raises blood pressure. And here's the funny thing about it is that we can't just simply look at one artery or one kidney, one artery or one segmental artery. We really need to take a sampling throughout the kidney, because here's the thing, this renin and angiotensinogen pathway is really quite powerful. And we could have a stenosis right here. And so only this part of the kidney, is seeing low blood pressure, and the rest of the kidney is seeing normal pressure, so it's not doing anything crazy. But this one alone can release renin and then go to angio. So one section of the kidney is capable of creating uncontrolled hypertension, one section of one kidney. So it's very powerful, and so therefore, when we look at the kidney, we can't simply just take one image, one pulse wave, and see what kind of waveform we have and say, oh, everything looks good. We actually have to take multiple looks at the kidney. So that brings me to the actual exam. If anyone has any questions on that, oh. Let's look at the actual exam. Yeah. The renal artery exam is in two distinct parts. There's the direct exam, which looks at, well, let's see, let's just write that out. Aorta and renal artery. And directly means directly. We're looking directly at those arteries. So with the aorta, now your book says you do a full aorta scan. That's fine. I never did it for this particular exam because it simply wasn't necessary, or wasn't part of our protocol, but that's fine. Go ahead and do a whole aorta check. But what you really want is a pulse wave at the level or just above level of renal arteries. Pulse wave at the level of renal arteries. In other words, what you're really wanting is what is peak systolic velocity. And we're going to record this. All modern machines have a built-in worksheet. So if you record this correctly, you don't have to do any math at the end. And if you don't record it correctly, or you're using an older machine or a machine that's not properly set up, then the math is simply one value over another value. It's just a it's a renal artery divided by aortic artery. So not exactly hard math, but still, it's better just to have the machine do it for us. So let's do a direct exam. This is step number 1. I guess I should put that there. Peak systolic velocity. And so, all right, step number 2, renal artery. Obviously, right renal artery, left renal artery. Prox, mid, distal, and if you see it, let's see, and of course, stenosis. Prox, mid, and distal, what is peak systolic velocity again? We're also going to look at the wave form. So peak systolic velocity and shape of wave, question mark. Okay. So let me back up a little here. I'm going to give myself more room for the second part of the exam. So we do a, let's see, at the level, I've got too much going on here, but so if I were to draw just a tiny little, you know what that is, obviously, that's a symbol that I'm doing a pulse wave here, so that's my aorta. And then when you do that in sagittal, and then you go transverse on the aorta so that your transducer, let's just look at the right side here. I have my more or less transverse plane. And from there, I should be able to find the proximal right renal artery, proximal left renal artery. You can go ahead and do both of them, even though you're going to start on the right, at least most people do. But if you want to get the left one done, you can. You just have to put it into the system correctly, so that it correctly calculates with the left side. So, but in any case, so I'm going to do a pulse wave. Well, obviously, in this person, I'm going to do one right here at the stenosis. But even if I don't see a stenosis, like I don't see one over here, that's my prox, and then a mid, and then a distal. Oh, well, I should probably say the mid and distal, you're not going to see from the abdomen or from the belly. So you could go transverse on the belly, you push down hard to get those intestines out of the way, and you get your proximal arteries. And then in order to get your mid and distal arteries, you're going to bring your transducer over to the side, and you're going to scan from the side, looking through the kidney, and as much as you can straight down the barrel. Always doing the best we can to have the smallest angle, Doppler angle. Never over 60, but unlike the aorta, the carotid artery, we stuck to 60. That's only the carotid artery. There is no other system I can think of where you stick to 60. It is actually better to be below 60. Having said that, very difficult because you're probably using a curved transducer, which does not steer. A curved transducer, it's very difficult to get a Doppler angle much less than 60. In fact, it's sometimes just getting to that point is tough. So 60 degrees or better, all the way from the aorta and all the way through through the renal arteries. So let's see. And that's pretty much it. So if you find a stenosis, great. If you don't find a stenosis, better for the patient. And look for the waveform. So, let's do a good waveform first. So let's see, I'm gonna use that little cheat bar here. This helps me draw something out fairly nice here. And we're gonna want a nice fast upstroke. And then we call this, I'm set up a little bit too much here. Good. And then the same thing over again. Okay, I'm just going to draw that much of it because you don't need to watch me do that. This little guy here, it could be the higher or it could be slightly lower, and I don't understand entirely why that happens. This is called ESP, and it's not predicting the future or knowing what you're thinking. It's ESP is early systolic peak. I'm not going to write that out. Early systolic peak is this little guy right here. Like I said, it can actually be the highest point. Here, let's draw it over here. Yeah, something like kind of that. Actually, I don't like that one. But in any case, an early systolic peak is an indication of very compliant vessels. Compliant meaning they probably don't have a lot of plaque in them. They're loose. They're what they're supposed to be. So this is good. It's a smiley face for your early systolic peak. You don't always get this. In fact, if you're at a 60-degree angle, probably will not see. Whoops, probably will not see the early systolic peak at a 60-degree angle. At maybe a 30-degree angle or less, you will see it. And that's important because some books tell you that you have to find the ESP. If it's not there, it's unusual. Well, no, you have to be at a really good angle because this is a very sensitive measurement, very sensitive finding. So this is, let's see, that's good. Also, low resistance blood flow to the kidney. In other words, there's plenty of flow in end diastole. So this is, let's see, we'll call this good or normal. We could find an abnormal. Well, you guys know TARDIS is not good. So let's see, TARDIS parvus, let's see. Oh. Well, it's TARDIS parvus, not good. What defines TARDIS parvus? Well, the rounded top. There's definitely no early systolic peak, but not only is there not an early systolic peak, there's not even really TARDIS means late. It means, and parvus is slow. So parvus is, but in any case, TARDIS is late. Well, that means the velocity for the time from, let's say, from here to here, this distance measured on a pulse wave is your acceleration time. This one over here had a much better acceleration time. Let's just put AT. Acceleration time on that one And you know what? I have to research. I think you actually only measured to the early systolic peak for acceleration time. Yeah, you know what? You probably do because it is early systole. So this acceleration time is much less than this acceleration time. That's kind of the numerical definition. Visually, we see as tardus parvis, but the numerical definition. So this acceleration time is greater than 100 milliseconds. This acceleration time is less than 100 milliseconds. So that's one thing we can look at. So low resistance, early systolic peak, if you have a really good angle, those are all good signs. Tardus parvis, and well, of course, other evidence of turbulence is a bad sign. An increased acceleration time is a bad sign. So these are all bad. This is all good. Just a quick note, just kind of interesting and somewhat useful to know. The waveform of the aorta there versus the waveform down here is different. That's just really cool. Let's start down here. Down here, the waveform is, let's see, we'll start the line up, can be down and back up, and then pretty much over, and then high resistance. And this looks like, I know you haven't done arteries going out into the legs yet, but this looks like extremities. Well, that's because at this point, the aorta is feeding mostly the legs. Some pelvic organs and such still in there, so it's not as not Wind-Kessel effect as much as the legs are, but there's definitely more of a high resistance. Whereas the aorta up here, well, yeah, it's feeding down to here. It's feeding the legs, but it's also feeding the liver, the spleen, and both kidneys, all of which are low resistance organs. So your waveform can be a little more not super low resistance because it is a combination of low and high resistance. So it's kind of it's a midway resistance. But anyways, that's just more of a, just so you know. And now you know. And of course, we're measuring peak systolic velocity there. And over here, if I drop down to here, peak systolic velocity. And what we're going to do is find, I guess I'll put it here, the renal aortic ratio. In other words, the renal peak systolic velocity divided by the aortic peak systolic velocity. And that's it. It'd be helpful if I remembered what the numbers are. Yes. Let's see, less than, so that ratio less than 3.5, and it's a ratio, so there's no units. That is good. Greater than 3.5 is bad. I hope that makes sense. So so the first part of the exam, I'll just repeat, we take, let's do a different color here so we can see this. We take basically 1, 2, 3, 4 measurements, more if per side. Well, aorta plus 3 on the right, aorta plus 3 on the left. Minimum. Obviously, if you see a stenosis or if you see something of concern, you take more, but a minimum is aorta plus proximate distal. Aorta, proximate distal. And that's the first part of the exam. I actually don't like that part of the exam because guess what? The renal artery is a lot smaller than the renal vein, which is running right next to it. It's surprisingly small. Well, your kidney is only about the size of your fist. And this is a pretty, the velocities in here are pretty good. So plenty of blood's getting into the kidney, but that actual artery is quite small. And it's, well, this is a retroperitoneal organ. It's way in the back. It's behind intestines. It's, this is very difficult. And there's honestly been quite a few times where I suspected there probably was a stenosis, but I just couldn't see it. Shadowing, gas shadows out a whole bunch of the artery, and the person's heavy, and it just makes it very difficult. So I find that to be the harder part of this exam, and I also find it to be so much less reliable that I actually like part 2 of the exam much better. Let's see, 1:52. I think this is a good time. Good time to take a break because now I can also give myself a little more room over here to write down part 2 of the exam. All right, so it's well, oh no, it's 1:52. 2:10. I've got some things to write down, so 2:10 will be good. I'll see you guys shortly. Dang nabbit. All right. So second part, I'm just going to quickly say this again. Second part of the exam, the better part, I think it should be the first part because it tells us what's going on downstream, because we're looking for a waveform analysis. In other words, we're going to be looking for tardus parvus or anything like that. We can look at segmental arteries. We could look at interlobar arteries. Your machine will oftentimes say arcuate artery, and that's a joke. You are not very unlikely scanning arcuate arteries. Now, having said that, we will do a superior pole and mid pole, which is a bit of an oxymoron. There's no such thing as a mid pole, but superior, mid, and lower. So, or inferior. Let's do that's an R. Anyway, inferior pole, just to be a little more medically accurate. And so we're going to scan this kidney. We're going to look very closely. And I don't care if it's in sagittal or transverse, whatever works. We're going to find an artery up here. And trust me, this patient's breathing. The kidney's going up and down every time they take a breath. And so what you do is you kind of have them take a breath in, hold it for a second. You figure out where this moves to. Let's say you're looking at this artery in particular, and they take a breath in, it's going to move an inch away. So have them take a breath in. You mark where it's going to be, and then you let them breathe. And you get everything ready. You get that pulse wave ready, and you get ready to hit start on the pulse wave. You have your color on, obviously, so you can see where to put the pulse wave. and you say, okay, take a breath in and hold it. Hopefully they take the same amount of breath in and not a different amount of breath in. Breath in and hold it. It comes down. You get your region of interest right on the blood vessel, and you hit start. And I don't care if you are struggling and you only get one waveform and the rest is missing because the patient moved. It's not ideal, but it's good enough, because it's not gonna, if it's one clean waveform, it is enough to at least let us know, was there tardius partus or not. So interlobar artery, we'll do, that's your superior pole or upper, sometimes we say upper, really all the same difference. Superior pole, upper pole, mid pole. Once again, we'll do a interlobar artery, because that is probably what you're looking at. If you're in the parenchyma, you're probably looking at interlobar arteries. We get that one, we get the best darn angle, and I mean, if your angle is 0 degrees, that is the best angle possible, and that's what you're shooting for. You don't care about here. 60 degrees in this situation, no. You don't want 60 degrees. You want closer to 0. And let's say we get down to the lower pole, and I am just having a hard time. My angle is really just not getting it. I can't get it. All right, fine. So down here, I'm just going to go ahead and do a segmental artery, because a segmental artery is feeding this interlobar artery. It's going to have the same waveform. It's going to be easier to see too. Prefer the lobars, interlobars, but a segmental is acceptable. And some people will do interlobars and segmentals. That's fine, whatever your protocol is. What we're looking for, of course, and oh, and by the way, don't bother with angle correct. Don't bother. That's the first time I ever told you to not bother with the angle correct. In other words, you don't have to sit there and figure out, your exact, how's the blood vessel going. There's 2 reasons for that. One, very hard to angle correct when you have a tiny piece of an artery on color and you're angle correcting on that. Are you really angle correcting, or you think you're angle correcting? That's one. It's hard to be accurate. And 2, angle correct it corrects velocities. We don't care about velocity. We're doing waveform analysis only. So don't bother angle correcting. Let's see over here. Over here, on that first part of the exam, you will angle correct, because velocity is, the renal aortic ratio is all about velocity. So you need accurate velocities. On the first part of the exam, you will angle correct. Over here, don't bother. You could do it if you want. It's not going to hurt anything. And if you're just in the habit of doing it, that's fine. But it doesn't matter, and it doesn't matter for 2 things. One, we're looking at waveform analysis. So does our waveform look more like? So that's another one. My early systolic peak is my higher peak. And it's also possible to have it's also possible to have an early systolic peak that is not the highest peak. I don't know why, but both are possible. Both are fine. So we're looking for your ESP. That is good. We're looking for, you probably won't be asked to measure it, but if you are, it's very easy measurement, the acceleration time from here to here, and that needs to be less than 100. Or you could just be eyeballing it. Does it look, eyeballing? Yeah. You could just eyeball it and say, is it a good looking waveform? Does it look like that, or does it look like that? Tardus parvis, that's bad. The other thing you can do, and you probably will be asked to do, and this is kind of, in a way, this is actually not even a part of the renal artery exam, but you'll still be asked to do it, so it is part of the exam. Let's just say this is an add-on. An add-on is resistive index, the RI. The resistive index is simply a measure of, oh God, I have to do this from memory, peak systolic velocity minus end diastolic velocity divided by peak systolic velocity. And that is from memory, so if I'm wrong, I apologize, but I believe that it is. I'm not going to write it down because I'm just doubling down. I'm dumb if I'm incorrect. In any case, resistive index, well, gives us an index of the resistivity. So, you know, and so resistive index is also another way of looking at. Well, let's see if we have an artery that has, and then the baseline is way down here. We have a lot of diastolic flow. Peak systole is barely any higher than diastolic. That is a very low resistance. It's going to have a low resistive index. If you have a waveform that looks more like this, that's a much higher resistive index. Yes, there's continuous flow, but the end diastolic flow is much closer to the baseline. That's a relatively high resistive index. The RI for the kidney, oh, I forgot to write the median range. It's like 0.5, approximately 0.56 to 0.64. That's from memory. Again, I don't know why I didn't write a couple of these things down. That's normal for a kidney. If you have a high resistance, if it is greater than, this I did write down, 0.8, that is an indication of renal disease, not vascular disease, more like some other kind of kidney disease. And just like a liver has low resistance until it has cirrhosis, and then the resistance goes higher, in a kidney with renal disease, the resistance goes up. And so a high resistance can be an indication of renal disease. Once again, not really a part of the renal artery exam. It's just kind of an add-on. And an unusually low resistance could be an indicator of a parenchyma that is starving for blood. And so that actually could be a indicator of a vascular problem, because if the parenchyma is starving for blood, then it wants more blood, so the arterioles open up, and then you have unusually low resistance. Once again, though, not a normal part of the exam. It is something that most people will do in the exam. But if you really think about it, it has nothing to do with renal artery stenosis. So let's just put all this in here. and we'll call this the add-on. Okay. So I hope this makes sense. Let me go over the second part of the exam again. Once again. Oh, and the reason I say it should be the first part, well, if I go through the kidney and I see an early systolic peak, or the least of which, low acceleration times, nice sharp peaks, continuous flow, looks like a nice R, and I measure the RI, that's normal as well, then I could pretty much assume that the aorta and the renal artery is normal. And so now, or maybe I'd be lazy and then I wouldn't do a good job. I don't know. But it just seems to me that if you start on the kidney and work backwards, you have a better idea. If you see tardius parvis in the kidney, now you know there's something going on upstream. In other words, the renal artery somewhere probably has a stenosis. So, that's nice to know that in advance. So superior, mid, and lower poles, you get 3 representative samples. Parenchyma is better. Interlobar is probably what you're looking at, even though your machine's going to say arcuate artery. Don't bother with angle correct because we don't care about the velocities here. Oh, velocities. I did have a... Okay, let's move back up here. Oh, so I know what I want to talk about. So we've talked about, or at least we alluded to, when we talk about stenosis, we're really talking about atherosclerosis, right? Atherosclerosis is the #1 reason. Let's see. #1 reason for a renal let's see. Renal vascular disease #1 is atherosclerosis. And that's usually a little more of men more than women. In fact, where did I write this down? I'll just make sure I... Yeah. So atherosclerosis, men greater than women. More men have athero of the renal vascular system than women. And then the #2, though, is fibromuscular dysplasia, FMD. That is women greater than men. Most of the people who get fibromuscular dysplasia are women. Let's see, I actually wrote, doink, and look how quickly I drew that. You guys didn't even see it happen. Fibromuscular dysplasia, same thing as that people can get in the, most likely the internal carotid artery, is a dysplasia, dysplastic growth of the walls of the artery, and it creates a beaded appearance. No plaque involved. However, once it gets bad enough, and this kind of, the walls kind of grow in like this, a stenosis can form. And then if a stenosis forms, it has the same exact effect as atherosclerosis. The Bernoulli principle says that the blood pressure is going to go down, and now that kidney is seeing less blood pressure, and now the left kidney on this patient is going to cause systemic rise in blood pressure because it thinks systemically the blood pressure is low. I think size is the only thing. Okay. Well, this part was a lot shorter than I thought. I guess I'm a little long-winded on the first part. Because really, there's only one more thing to say, and I am open to all sorts of questions, guys, if you have any. But let's just finish up with one last thing. When we measure the kidney, we measure the length is the most important measurement of the kidney. We do width and height as well, but the length is the most important. And a discrepancy between the two kidneys of more than 2 centimeters is an indication of chronic renal artery stenosis, possibly even renal artery occlusion, because the kidney can still be fed from other arteries that aren't really like, there's a superior artery that goes to the adrenal gland, and that could create anastomosis, or it could create collaterals in order to feed a kidney. So the kidney's alive, but basically useless. So if you have one large, one small kidney, that is an indication. Let's just write it down here, a little more room. Let's get up a little closer. Okay, this last bit of area I have down here. Size, discrepancy, between right kidney and left kidney of more than 2 centimeters. Bad. The smaller one is diseased. The smaller one, and probably not getting the blood supply. The other one is just saying for an adult length of, let's see, less than 9 centimeters is also bad. But I don't like that because some people are just really small. Really tiny people are going to have tiny kidneys, and really tall people will have tall kidneys. That's just how we're built. So that is something, and that is part of the exam. When we do this exam, the actual exam is as explained. However, almost everywhere you work, a basic kidney measurements and a sweep through will also be required as well, because they do want to know, are there any masses? Is there hydronephrosis, which is urine backup in the collecting system, is hydronephrosis, length discrepancies, tumors, and that kind of stuff. So you will go through the kidney, but it's perhaps not as much of a thorough kidney exam, because what we're really interested in is the vascular nature of it. Um, Really, the only other thing is, these patients, of course, they need to be NPO. No, we're not worried about their gallbladder. But I did, man, I had to see a patient. He didn't know he had to be NPO. And I'm like, just come on in. I'm not looking at your gallbladder. You might be a little gassy in a postprandial state. So, but I'll work around the gas. He wasn't a big guy, so I figured I'd just push and get around the gas. Well, totally wasted, totally useless exam. I should never have let him in the room. The reason being is he was gassy, but it wasn't the gas that was really the problem. It was his very strong peristalsis of the intestines and the gurgling and the all that. Trust me, your machine is going to recognize that as flow. And so every time his stomach or his intestines moved and bubbles of gases and food went through his intestines, it caused a nightmare on my screen, and I couldn't do the exam at all. It was a complete waste of time. So definitely your patient should be in the NPO state for that reason. But and then you warn them, this is a long exam, and please cooperate. But yeah, that's about it. Any questions on this exam? Any questions on the ratio and what does it mean, or the resistive index, which I did from memory. So maybe all you guys are thinking, I just quickly double check and that's it and say that wrong.
And whenever you get done with that, I do have some questions about the exam.
Okay, what you got?
When you're doing the aorta and the artery, is it similar to how we did the because I noticed a lot of it's been talking about the spectral Doppler. From an image standpoint, are we getting as many images as we did in the carotid, like 3 at each point?
Well, no. I guess it actually is similar to the carotid. With the, let's see, I guess the aorta, there's only one. Each renal artery, a minimum of 3. 1, 2, 3. So that would be part 1 of the exam is 1, 2, 3, 4, 5, 6, 7. And that's it. And that's the first part of the exam. You add the second part of the exam, 8, 9, 10. I kind of messed that up. 11, 12, 13. So you get good images.
God damn, that's a lot of.
Oh, that's well, so 13 Doppler images plus you're going to want some grayscale imaging in there as well. So maybe double that and call it 20 or 26 images.
And
this is harder than a carotid by a long shot.
Yeah. And when you get to the inner lobar arteries, you're just doing one of each set, one of each pair, I guess you'd say.
Yeah, because chances are you're not going to see. There's pictures that you can find on the internet where the kidney is just lit up like unbelievably. Those are the most ideal conditions possible. Chances are you're going to see on a lot of people a little bit of blood flow, and gosh, you're going to have a real hard time down here, and you're going to just struggle. But you put your pulse wave wherever you see color, and you just get it. You know,
And are you using just a regular color Doppler, or is it okay to use the power Doppler in this one?
You can use power. And actually, that's not a bad idea since it's better at slow flow. Velocities do decrease as the farther you go out. They start like at 100 centimeters per second, more or less in the aorta, then down to 90 to 80, down to, I wrote it down. I decided not to burden you guys with it. Down to 50s, 30s or 50s in the segmentals, and down even less to 10 or all the way down to like 10 centimeters per second, all the way out here at the far end. So yeah, your velocities do go down. So yeah, power.
I had that question about that when we were doing vascular in the last semester. I remember I was wondering how the velocities got lower, even though the vessels got smaller, which it seemed like it should be opposite, but I didn't take into account the fact that they branch off. So
yeah, that's exactly what happens here too, is that even though they're smaller and you think because of Bernoulli's principle, that means they have to go faster, but they get smaller because they're branching. And so, and now that they're smaller, Poiseuille's principle is more of a factor because smaller diameter, less volume flow. But yeah, let's see. Renal aortic ratio. No, I want RI. I want RI. I know it's right here under my nose. I just read it. There's more than one way to skin a cat. Where's my... Peak systolic velocity minus end diastolic velocity divided by peak systolic velocity. Yeah, so good. I did say it correctly. Here, let me just write that down too. I'm gonna have to write it all the way up here though. Oh my God. Peak systolic velocity minus end diastolic velocity. In other words, this guy minus that guy divided by peak systolic velocity. All right. All right.
Is that like when you have the double peaks? Is that why you're dividing by two peak systolic velocities?
No, it's just the way the index is created. There's resistive index. There's the pulsativity index. That's PI. I don't know if that's actually right here.
Which formula is that one?
The pulsativity index is actually...
No. The one you already wrote out.
Oh, this is resistive index, RI. And so for kidneys, that's what they use. Different researchers use different indexes for different things. And honestly, it's getting so much into the weeds as to why they use a different index. Like a pulsatility index is very similar because it's going to give us the same thing. Let's see. Oh, come on. Peak systolic and diastolic. Really, that's what I need right now is a advertisement that I just clicked on. And I've got so many things going on in front of me that I can't. Anyway, there's a peak systolic, there's pulsatility index, which is basically, I can't see, it's peak systolic minus I think I see, I could barely see it around this advertisement, which I can't get away because I can't get it away. Hold on, I do have a mouse. Sometimes I don't have my mouse attached. Okay. Peak systolic minus peak diastolic divided by the mean. So, sometimes pulsatility index is used, not in the kidneys though, so that's why I didn't bring it up before. And there's all sorts of indexes. Sometimes it's just a ratio of peak systolic velocity minus end diastolic velocity. Or divided by the two. Anyhow.
And I didn't mean to take us all the way down a rabbit hole. I was just wondering how you got where the two peak systolic velocities come from, because it seems like they would cancel out.
Yeah, no, it's, let's say this is 100, and then this is 50. Then it would be 100 minus 50 divided by 100. So it's the same peak systolic velocity. It's kind of it's just a ratio. It's just a way of doing that. So.
Gotcha.
Yeah. So I guess this ratio would be 0.5, right? Am I right? 100 minus 50 divided by, which would be 50 divided by 100 should be 0.5. Mm-hmm. So anyhow, and that would be a good ratio. It could be a good resistive index for the kidney, because I do believe, I did this from memory, but I do believe normal kidney is around 0.56 to 0.64 as far as and that doesn't mean if it's 0.54 it's bad, or 0.68 it's bad. It's just, this is kind of a general idea.
At what point on the lower end of that spectrum would you start suspecting that the parenchyma is starving for blood?
Well, numerically 0.8. For the lower part.
Yeah, I was like, what?
I don't know. Because it's already such a low resistance to begin with. I mean, certainly if you're at 0.4, that's would be suspicious, because that would be like, I mean, the difference between peak systole and end diastole would be so little, it'd be practically steady state flow at some point. All right. Anything else? Any other questions? All right.
Good.
All right. I think this is pretty good. This was a lot of information. I strongly suggest. I think I have to put yesterday's up on the web too, up on YouTube. I'll put I'll put a couple of more up on YouTube. Make sure we're all caught up on that. Tomorrow, we're going to talk about kidney again, except this time It'll be more of the overall architecture of the kidney, which you already have a pretty decent idea about, but there's a little more detail in here we'll fill in. And then after that, we start talking about renal function and renal diseases, which honestly is not as, there's a lot of them, but it's not as bad as like the liver, because the liver was more of a laundry list, and this is more of, I don't know, grocery. Still a list, but it's, I think it's a little more interesting. Tomorrow, so we start on regular kidney. Afterwards, gallbladder, biliary examination. I'm not done with it. I don't know exactly how many questions, but we'll do that. We'll give you you guys can vote, but at least 20 minutes to a half an hour of a break between class, and then I'll open up the exam. Obviously open book and all that, but it's a good idea to know where your notes are, or have good notes, so that you're not struggling to find information. Just like I was struggling to find information here. When you need it fast, you can't find it. So, and that's what happens on tests too. All right. We're ready, guys. We will see you.
All right.